In this chapter, we're going to take a look at special relativity. Okay, so to begin with, we need to talk about frames of reference. So what this means is that motion is relative. And what I mean by that is if you're in a car, for example, and the car is traveling at 60 miles per hour, that 60 miles per hour has to be relative to something. Now, it's understood that it's relative to the Earth. But the speed of the car, if it was relative to the sun, would be something totally different. Okay, well, what about light? What is that relative to? We know the speed of the light is 3 times 10 to the 8th meters per second, but relative to what? Well, in the early part of the 19th century, physicists postulated something that was called ether. And they said that must be that the speed of light was relative to this ether, which permeated all of free space. And Michelson and Morley did this little experiment right up here. And essentially the experiment was this. If the Earth is going in this direction, then if you measured the speed of light in this direction, the Earth would be moving through the ether in this direction, then the speed of light should have a different value measured this way than this way, because the Earth is moving through the ether in this direction. So they did some very carefully managed experiments, and they found that the speed of light was the same this direction as it was in this direction. Now, this experiment was repeated over and over again by not only by Michelson and Morley, but many other experimenters as well. Everybody always got the same results. The speed of light was the same in this direction as it was in this direction. And they found this extremely puzzling. So Einstein comes along with his special relativity. And special relativity is really based on 2 postulates. Now, the first postulate is that the laws of nature are the same for all frames of reference that are moving uniformly. So what that means is, if you are in, let's say, a spaceship, and you are moving uniformly, in other words, constant velocity in a straight line, there's no experiment that you can do to determine whether or not you're moving uniformly or that you are moving or you are at rest. For example, if you open up the windows in the spacecraft and looked out, you may see stars going by you. But you really don't know if you are moving relative to the stars or you are at rest and the stars are moving relative to you. Either way, they'd be moving backward. So that was the first postulate. No experiment that you could do to determine whether or not you are at rest or moving uniformly. Now, Einstein took that a step further and said that those 2 frames of references are equivalent. Okay, now here's the second postulate. The speed of light is constant. Okay, in the last slide we talked about Michelson and Morley. Michelson and Morley were trying to find the speed of light differing as it moved through the ether. Einstein says, forget the ether. The speed of light is going to be constant no matter which direction you measure it. It's always going to be the same, whether you're moving it parallel to the direction of the Earth, perpendicular to the direction of the Earth. The speed of light is always constant. Now, one of the weird things about these 2 postulates of special relativity is that 2 events that are simultaneous in one frame of reference need not be simultaneous in other frames of reference. Okay, let's refer to this little diagram here to see if we can understand that. So we've got a moving train here, and we've got a guy there on the inside, and we've got a light bulb, and the light bulb is switched on. We see a beam of light go this way, a beam of light go this way. The guy inside the train sees a spot of light hit on both sides of the train car at the same time, simultaneously. On the other hand, if someone who is out here, different frame of reference, sees the car go by, then as the light bulb gets switched on, the light hits this side before it hits this side. Why? The train is moving in this direction, so light has less distance to travel to hit the back of the train over here than it does over here. So it's going to hit here first and then hit here. So in other words, he sees these two events as not being simultaneous. And that's one of the things that occurs as a result of special relativity. Time dilation is one of the most fascinating parts of Einstein's special theory of relativity. And we'll see if we can get some understanding of what it is. All right, so we've got a rocket ship over here. And the rocket ship is moving with a certain velocity. We've got a guy inside the rocket ship here. And he's got a couple of mirrors here and here on the bottom and the top. And he can watch the light pulses as it goes from the bottom to the top. Obviously, light travels so fast. You couldn't really do that, but if you could. Okay, so he could actually do a little experiment, measure the speed of light, and of course, speed of light would have to come out to be 3 times 10 to the 8th meters per second. All right, now, under the line here, it shows the path of the rocket ship, but we see an observer here in a different frame of reference. He's on the Earth, and he can actually see into this rocket ship. So as the rocket ship is moving, this observer sees the path of light not go directly from the bottom to the top, as the person on the inside sees it. He sees it traveling this much longer path over here, because by the time the light gets to the top of the rocket has moved to this position, so the path of the light is much longer. And then, of course, the same thing as the light goes from the bottom mirror, of the top mirror to the bottom mirror. Okay, so if the distance is longer, the only explanation, since speed of light has to be constant in all frame of references, is that time is slower for this person inside the rocket ship. So he's traveling this longer distance, but the time has got to be slower. And the slower time is what's called the time dilation. It's got to be that way so that every person can measure the speed of light to be the same thing. So from the perspective of this observer on the Earth, this moving rocket ship, the time, the clock inside it, has to run slower. Now, we've made this little light clock here as an example, but same thing would hold true for any kinds of clocks inside the rocket ship. All clocks are going to run slower as they're in motion. All right, so we go back to this, down here to this equation. Now, we're not going to do much to this equation, but I would like you to just fool around with the formula just a little bit, plug in some values. First of all, this effect of time dilation really only is appreciable when the velocities here are extremely large, when they're approaching the speed of light. Normal velocities, well, you can calculate what the time dilation is, but you'll find out that it's so small that, it would be impossible to measure. But it does exist, and if we'll just take a little quick look at this formula here, and we can see, first of all, that if the object is at rest, the two velocities are the same. And that's because if the object is at rest, v is 0, that makes this whole fraction 0. That makes this just 1. The square root of 1 is 1. That makes tv and t 0. The same thing, no time dilation. On the other hand, when v is some value, then this ratio becomes some number. When you subtract it from 1, that's going to make the denominator, and take the square root, that's going to make the denominator here some number less than 1. That's going to make this time actually larger than the proper time. Now, this is not all theoretical. There is experimental evidence to back this up. One example, they mention it in the textbook, but I'll mention it again, has to do with the half-lives of particles. Now, particles have half-life, and all that means is that that's the time that it takes the particle to decay on average. So if you take a whole bunch of particles and figure out their half-life, it'll always come out to be the same thing. But they found that particles, these same particles, have a known half-life. If they're moving extremely large, fast, in particle accelerators, their half-life becomes longer. In other words, their little internal clocks actually run slower than they do when they are at rest. Another consequence of the theory of relativity is length contraction. And as we'll see, length contraction is really another face of time dilation. All right, so let's use him as an example, an astronaut who is in a rocket ship and he's going to travel to a distant planet. Let's say it's 1 billion miles away. So he gets in his rocket ship and he starts his journey, but he measures that distance to be something less than 1 billion miles because of this issue of length contraction. Okay, so he arrives at the planet, and let's say it takes him a year. Okay, meanwhile on Earth, they don't see this length contraction because they're not in motion relative to the astronaut. And they see that it's the full 1 billion miles, but they agree that it took him a year to get there, and that's because his clock ran slower. And in other words, they see the time dilation as opposed to the length contraction. So the astronaut that is in the spaceship sees the length contraction. On the other hand, the observer sees the time dilation. They both agree it took a year to get to the planet. Okay, the last thing I'm just going to say a few words about is E equals mc squared. Of course, very famous formula. First of all, what is it? It's the mass-energy conversion formula. With this formula, we can convert quantities. We can calculate quantity of energy that can be released from a given amount of mass. Perhaps the most important thing about this is the fact that it shows that mass and energy are indeed equivalent. In other words, they're just two forms of the same thing. And small amount of mass can produce just a huge amount of energy. If you just do a little bit of calculations with this, we know that the speed of light, 3 times 10 to the 8th, extremely large number. When you square that, you get 9 times 10 to the 16th, just very large number. So just a tiny quantity of mass can release a significant amount of energy. And make sure you read that section of the book that talks about this mass-energy conversion happens in all situations where energy is released.